Hello, everyone. Welcome back to the second edition of Math 135 Coronavirus Edition. Today, I want to give you a couple reminders. I hope that the lectures are going okay for you so far. A couple reminders today, web assignment is due. Reminded this is material you learned before spring break. So let me know if you have questions on the forum or via email. Today, we're not going to have a worksheet. What I want you to do is to take notes of the lecture and then scan in your notes and upload those, showing all of your work. That's how you'll get credit for today's class. And I'll scan through the notes to make sure that you actually wrote down the notes and worked on any problems we had to work. All right, let's get started then. So last time you took these dice rolls and you averaged them and you came up with a new histogram. And so we want to take a look at that again today. So first, we're going to start with a normal distribution. You can see at the top that this is a normal distribution, and we're going to take samples from it and then take the sample mean. So let's take a sample, see what happens. And we can take some more samples, but maybe a couple samples don't quite tell us the whole story. So we can just take 10,000 samples really fast. And I want you to pause the video and describe what's different about the black distribution at the top and the blue distribution below. All right, now that you've had the chance to think about that, you can pretty clearly see that the top distribution is symmetric and the bottom distribution is symmetric. They have the same mean, but you see that the standard deviation is smaller of the distribution below. So they're both normal, but the one below has a smaller standard deviation. Okay, well, let's take samples of size 5 instead of size 2. I want you to pause the video for a second and think about what you think is going to happen if I take samples of size 5 and calculate the sample mean, whereas before we took samples of size 2 and calculated the sample mean. All right, now that you've had a chance to do that, we can take a couple samples, and then we can just simulate 10,000 of them. What happened? Well, you see that this distribution has the same mean again, but the standard deviation is even smaller. See, we can compare drawing samples of size 2 to samples of size 5, and we can do 10,000 samples, and we see that the sample of size 5, that normal distribution is more concentrated. And if you go size 25, I bet you can guess what will happen again. It's even more concentrated. So we see that if we start with the normal distribution at the top in black, we take a sample of size 5 or 25 and average it, and we do that a lot, and plot those sample means on the histogram, we get a normal distribution again, except it's more concentrated. The standard deviation is smaller. So that is the first theorem from today, talking about what happens when you take a normal distribution, let's say height of men in the United States, and you take a sample and you average them. So if you do have a normal distribution with mean mu and standard deviation sigma, then if I take sample means and I plot them on a histogram, I see that it's also going to have a normal distribution, and the average is going to be the same as the original distribution. But the standard deviation will be smaller. So you see here that the standard deviation, let me identify it for you. You see the standard deviation is the old standard deviation divided by root n, where n was the sample size. So this is going to be very helpful for us. It's a little bit more probability theory that we have to learn, but this will be very, very helpful for us when we need to learn about confidence intervals. Okay, so let's elaborate a bit more. What is this telling us? It says that if we have a normal distribution, let's say it's men in the United States, and we're looking at their height, and we take a sample of size n, then the standard deviation has gotten smaller, as we see right here, and the mean has stayed the same. You should be reminded of the little activity we just saw, where the Means all stayed the same, but the peaks got more concentrated. That is, consistent with the standard deviation getting smaller. All right, so let's go back to that slide. What this means is z, which is the standard normal variable, has a new formula because we have to divide the standard deviation by the square root of the sample size. And so this is going to factor in as we compute some new probabilities. Okay. So let's do an example. So our population X has a normal distribution with mean 20 and standard deviation 3. So let's picture this as the number of minutes the average student can pay attention to an online video with standard deviation 3. So this is the time in minutes. And we take samples of size 16. We want to describe this distribution of X bar. Well, that means we need to know what's the mean and what's the standard deviation. Well, if you look back at the previous slide, you'll see that the mean is the same as the mean of the underlying population. What that means for us is that if we take samples of size 16, on average, they're about 20 when I take their sample mean. However, the standard deviation has decreased. See, I have to divide it by the square root of the sample size. That's what we see right here. And so what I need to do in order to calculate the standard deviation of my sample means, I need to take the standard deviation of the population and divide it by the square root of the sample size. All right. So now I can use that to find the z-value corresponding to X bar. So let's see what that's going to look like. The z-value, if you recall, is the X bar value minus the mean of X bar over the standard deviation of X bar. And we've calculated all those things on the right. This actually is 0.75. I can't really see it, but that's 0.75 right here. So our X bar value is 19 minus 20 over 0.75. And if we compute that, we should get a value of negative 1.33. So that's the z-value corresponding to X bar. This is the same process you did before with normal distributions, except now the standard deviation gets changed a little bit because we're taking samples and averaging them. So we need to find the probability that X bar is less than 19. Well, the probability is the same as the probability that z is less than 19 minus 20 over 0.75. That's the z-score right here. That's what we've been computing in the past. This whole expression is the z-score. And so this is the probability that z is less than negative 1.33. So how do we find that? Well, I think you know the answer. We look it up in the normal distribution table. So let's look that up in our normal table to get the answer. And we look at negative 1.33. And what we should get, negative 1.33. 0.0918. So if I go back here, this should equal 0.0918. And that's the probability. That says that if I take a sample of 16 students and average the amount of time they can pay attention, to an online lecture, the probability that that average is less than 19 minutes is 9.18%, or 0.0918. All right. So don't fret, we're going to do another example, and I'm going to give you a few minutes to do it before I show you how to do it. All right, so let's try a new one, and I want you to pause the video and work this one out. I'll work it out quickly once you've had a chance to do it, but I want to make sure you know how to do this because you're going to have a worksheet over this on Monday. So pause the video and work this one out. All right, now that you've had a chance to work it out, let me show you how you can figure this out. Well, we know that mu x bar, we're taking samples of size 49 from a population with mean 15, is just the same as the mean from the population. That's 15. But the standard deviation of our sample means is equal to the old standard deviation divided by the square root of our sample size. So that becomes 14 over the square root of 49, which is 2. All right, so now we need to find the probability that our sample mean is between 15 and 17. So this should equal the probability where we put the z-scores here. And this is the probability that 0 is less than or equal to z, less than or equal to 1. So how do we calculate this value? Well, you can probably guess that I need to look it up in the normal distribution table. So I need to look up 1 in the normal distribution table, and I need to look up 0. So if I go to my table and I look up the number 0, I get 0.5. And if I look up the number 1, I get 0.8413. So those are the two probabilities that I'm going to subtract. And so this is the probability that z is less than or equal to 1 minus the probability that z is less than or equal to 0, which is 0.8413 minus 0.5, which is 0.3413. So that's the probability that my sample mean when I take samples of size 49 is between 15 and 17. All right, so I hope that has made sense so far. If not, go ahead and rewatch the video. But in all of these cases, our underlying population was normal. So this would apply to things such as height, but it might not apply to every situation. So the question is, what do we do when X does not have a normal distribution? And for that, we're going to look back at our distributions from before, except we're not going to start with a normal distribution. We're going to start with a skewed distribution. All right, so we're going to do the same thing as before. We have this kind of skewed distribution on the right that we're going to take samples from and take the sample mean. So let's take samples of size 2 and plot it. And let's just do 10,000 samples. And I want you to pause the video and analyze what is the same and what is different from the distribution on top. Well, now that you've had a chance to think about it, the distribution on bottom in blue is still a little bit skewed, but it's not as skewed as it was before. The means are the same, but the standard deviation of the blue distribution is a little bit smaller. So I want you to hypothesize what will happen when I take samples of size 5 and not just size 2. All right, let's do an example. All right, so what do we see? Well, from the last time, we see that, let me get this to be a marker color. Okay, so this is what we did last time right here. That was samples of size 2, and that one was skewed. But what do we see here now in the new case? In the new case, we see that the mean is still the same, but the standard deviation is smaller, and the distribution is less skewed than before. All right, well, let's try something else. Let's try changing this to a bigger sample size. I want you to pause the video and try to guess what's going to happen. All right, now that you've had that chance to guess, let's find out. What do we notice? The mean is still the same, but the distribution is almost symmetric. It is almost symmetric. So we took samples of size 25 in bottom, and we took the sample mean, we plotted it. We took the sample mean, we plotted it, and the distribution we got was not skewed at all. It was almost normal. And that is what we call the central limit theorem. So the central limit theorem says that it doesn't matter what our population looks like. It could be skewed, it could be uniform, it could be symmetric, it could be bimodal. When you take the sample mean and take a big sample size, plot it on the histogram, take a big sample size, take the sample mean, plot it on the histogram, and you do that a bunch, the histogram that you obtain looks normal. It is approximately normal. This is the most important theorem of this class that allows all statistics to work that you're going to encounter. Things with p-values and confidence intervals and hypothesis testing, everything you're going to see in your psychology classes, your sociology classes, your business classes, all rely on this central limit theorem. It is the most important theorem in intro stats. So what this is saying is that if I take a sample that's big enough, I can pretend that my distribution of x bar is normal. And the question is, how big a sample size do I need? Well, what we're going to use is, if our sample size is at least 30, then we can always use the central limit theorem. So if we do have a sample that's at least size 30, then we're going to assume that our x bar distribution is normal approximately. And the mean is mu, and the standard deviation is the standard deviation of the population. This is the population standard deviation. And this whole thing is the standard deviation of x bar. These are the same things that you encountered before when our underlying population was normal. They still hold true as long as our sample size is at least 30. So let's do an example where we can use the central limit theorem to make a similar kind of calculation. So here, we don't know what the distribution looks like. So let's take a look here, and let's say this is the number of hours on average these students are spending on TikTok per week now that you're on break. So this is not a normal distribution. We've got average of 15 hours a week with a standard deviation of 14 hours. Some people are spending a lot of time on TikTok. So I take a sample of 64 students, and I want to know what's the probability that my sample mean is between 15 hours in a week and 17 hours in a week. So I can use the central limit theorem because my n is bigger than 30. N is bigger than 30, which means we use the central limit theorem. So what does that mean? Well, we take our mean from before, that is just 15, and the standard deviation is the population standard deviation over the square root of the sample size. So this becomes 14 over the square root of 64, which is equal to 1.75. All right, so now I need to calculate my probability. So the probability that my sample of 64 students spend on average between 15 and 17 hours on TikTok in a week, we need to find the z-scores, just like we did before. All right, so almost done. And the right here, I believe what we get is 1.14. Okay, this is 1.14. And what we need to do now is look up in the table what we get when we have 0 and 1.14. All right, so let's look at our table. And what we notice is that when we look up 0 on our table, we get 0.5. And when we look up 1.14, we get 0.8729. So we take these numbers and we go back to our problem from before, and this will equal, let's see if I can write it out, 0.8729 minus 0.5, which is 0.3729. Sorry, it's a little cramped down there, but that answer is 0.3729. And that's my probability that if I took a sample of 64 Lee students and I took their sample mean for the number of hours they spent on TikTok in a week, it would be between 15 hours in 1 week and 17 hours in 1 week. All right, so now you can see how even if we don't know anything about our underlying population, like I don't know what, if I plotted a histogram of the number of hours you all have spent on TikTok over spring break in a single week, I don't know what that would look like. It would probably be skewed right, but I don't know. It might be bimodal skewed right. But I do know that if that's my mean of 15 hours and that's my standard deviation of 14 hours, this will be the probability that for a sample of size 64, the sample mean will be between 15 hours and 17 hours. All right, well, let's take a look at a non-example. So the average time a college male spends on Twitter each day is 90 minutes with a standard deviation of 45 minutes. What is the probability that if I sample 5 random men, their average time on Twitter will exceed 100 minutes? Well, I don't know what to do here because I don't know anything about the underlying distribution. We do not know about the distribution of the amount of time that men spend on Twitter in college. We know the mean, we know the standard deviation, but it could be skewed right, it could be uniform, it could be symmetric, I don't know. And our sample size is too small. Sample size is 5, which is less than 30, which means we cannot use the central limit theorem. We use the letters CLT to mean central limit theorem. So in this case, since I don't know that the underlying population is normal and my sample size is not big enough, I cannot conclude anything about this probability. So what you see here is the central limit theorem requires us to have a sample of size 30. Now, I had you take so many samples for your surveys. Let's say I want you all to have at least 100 survey responses because when you break it down to demographics, let's say men versus women, I want to make sure that you have at least 30 men and 30 women. Or if I break it down to freshmen and upperclassmen, I want to make sure you have 30 in each demographic group because you need that to use the central limit theorem. All right. If you have any questions, please either post on the forum email me, reach out to one of the TAs, and be sure to take your written notes and scan them in using the Apple app or whatever app you have on your phone to scan them in, or a scanner if you have one at home. Uh, that way, because taking pictures makes them look crazy sometimes. So the scanner uses your camera, but it makes it look a little bit better than just taking a picture. So let me know if you have trouble doing that. I'm happy to help. And then that, on Monday, you'll have a worksheet. But today, what you have to do is do your web design and turn in a copy of your notes from today. Let me know if you have any questions. Enjoy your weekend.